All right, it's high time to crack the business case. Let's start by taking a look at the net we are going to deal with. We have an input layer consisting of 10 units. Those are the inputs from our CSV. There are only two output nodes as there are only two possibilities, 0 and 1. We will build a net with two hidden layers. The number of units in each layer will be 50, but as we know very well, this is extremely easy to amend. Therefore, for a prototype of an algorithm, 50 is a good value. 50 hidden units in the hidden layers provide enough complexity that we expect the algorithm to be much more sophisticated than, say, a linear or logistic regression. At the same time, we don't want to put too many units initially, as we want to complete the learning quite fast and see if anything is being learned at all. All right, let's start coding. The first thing we need to do is to import TensorFlow. We didn't need it so far, so we did not import it. Cool. Throughout the entire course, we claim TensorFlow code is extremely reusable. We will now prove that is in fact true. Let me copy the MNIST model until the epoch loop. I am sure you are already familiar with this code. We are going to need a couple of adjustments. First, we know that our input size is 10 and not 784. The output size is 2 instead of 10. As we discussed a few seconds ago, I will leave the hidden layer size at 50. Then we have our good old reset default graph method, which will let us train the model from scratch simply by rerunning the cell. All right. Then we have the placeholders containing inputs and targets. I will change the targets type of data to int32 because the targets are zeros and ones. They are integers, and it makes sense to declare them as such. Keeping them as floats should work perfectly fine too, but it just doesn't seem right to me. Okay. The model itself is exactly the same. Everything is parameterized, so no adjustments are needed. There are two hidden layers, as in the MNIST, and an output layer, which is reached through a simple linear combination. The activation function of both hidden layers is ReLU, while the activation function for the output layer is incorporated in the loss through the softmax cross entropy with logits loss. Then we find the mean loss using the reduce mean method. The next two lines of code define the accuracy variable. They remain unchanged and serve the same purpose as before. The optimization will happen using the atom optimizer with a learning rate of 0.001. Note that, once again, we are building a model with suboptimal hyperparameters, and it will be up to you to fine-tune it later on. All right. After declaring the interactive session and the initializer, we prepare for initializing the variables. We will keep the batch size at 100. This time, though, we don't need the batch's number. Remember that we incorporated it in the class. The class takes care of batching. It just needed the batch size. So, I'll remove the corresponding line of code. Similarly, the early stopping mechanisms may remain the same. I'll change the max number of epochs to 50, as I already know how the algorithm will behave, and 50 is a better cap. Cool. We didn't need to change much. And trust me, this will yield a great model. Take a moment to appreciate how we're reusing 99% of the code for entirely different problems, digit recognition and customer conversion. This is the incredible advantage of using frameworks like TensorFlow. Time for the first major difference. In one of our first lectures, we said that around this time we would normally load the data. In the MNIST example, we use the TensorFlow data provider. Here, though, we pre-process the data on our own, so we will need to use the tools we developed to load the data. Let's declare two variables, train data and validation data. They will both be instances of the audiobook's data reader class. Train data equals audiobook's data reader with two arguments, train and batch size. So, train data is an instance of the audiobook's data reader class. Let me scroll up to the class. The train data variable we called was just loaded with the data from audiobooks data train.npz. It will take 100 samples at a time, as the batch size is 100. All right. Analogically, validation data equals audiobooks data reader with argument validation. We are all set. We can now create the loops that will train our algorithm. See you in the next lecture. Thanks for watching.